All right, I'm back from a rather lengthy lunch break this time. So I'm going to be back working on questions again. I think I was on 6.5a here. I've been doing like a little recap every time I start just so people know what I'm doing. Basically, I went through the class once, meaning that I watched all the lectures once, and I've done all the problem sets once. The problem sets were really hard. I didn't get most of them right the first time. It's been a lot of work. So this sometimes happens in a class where it's just very challenging, and so I have to do more work to get to a level where I feel confident with it. And so what I did after I finished the first pass of the problem sets was basically I went through, I made this document here where I went through each of the problem sets and I just wrote down concepts, techniques, ideas that I didn't quite get. And then I took all of these things and sort of reorganized it into this document here, where I have 3 columns: concepts, facts, and skills. And I also put up here questions that I wanted to either do. The circled ones I hadn't done for whatever reason in the first pass. And then the ones that are not circled are ones that I did do, but I would like to do them again, try them again to see if I get it this time. And so I took about a day and a half, 2 days maybe, working on some of these concepts. You can see a lot of them are crossed out because I did some kind of finding technique or I did some work on them. The facts here, even though most of them are not crossed off, I did do some stuff here and I made some flashcards, which I have here, which maybe I'll go through quickly right before I start working on the questions again. But there's not that many. There's maybe like, I don't know, 10 here. So for a class like this, you don't need to really do that many flashcards. There is a few things to memorize, but I mean, I'm mostly memorizing them through the context of actually working through the problems. So there were just a few kind of little tricky things that I found it hard to memorize that I'm doing there. And then the skills here, some of these I did Feynman techniques for, so integrating by parts, Taylor expansion, just so I could understand what was the reasoning behind the techniques. Some of these I decided not to do, and then other ones, of course, I'm practicing them when I go through the set again. And I did cross some things off, but I also added some things. So this is from going through the second pass now. I've made a little bit of a better analysis of what things I wasn't doing that well. So what I'm going to work on now is just continue to work through these problem sets. I'm a little over halfway, I think. Yeah, a little over halfway. And I've got the rest of the afternoon and 2 more days to try to work through this and also get through some of this. And then I think Monday, Tuesday, I'm going to just be working on prep for the exam. So I'm going to see how far I get on Friday. And then based on how I'm feeling at the end of Friday, like how well these things go, how confident I'm feeling, I may do a little bit of work on the weekend. I haven't quite decided yet. It probably won't be full time, but I did want to cover some of these, and I'm just not sure whether I'm going to get this all finished this week. So we'll just sort of see how things are going. A few questions. Christopher's asking, do I ever feel like I might forget your understanding? Well, of course you forget. You forget understanding just the same way you forget other concepts. It's not that you don't forget understandings. It's just that what an understanding is that it's usually taking a lot of different pieces and kind of putting them together into a more cohesive whole. So just by the fact that they're taking separate little pieces and bringing them together into one relationship, one understanding, one kind of intuition or idea makes it easier to work through. So you can still forget that whole thing, but it's a little bit harder to forget. And so that's why I tend to focus on understanding, because if you can take a bunch of facts that seem unrelated and put them together into one complete picture, it'll be a lot easier to do. So doing questions is the way to maintain memory, period. Active recall is the best way to remember things. There are specific tools that can help with more specific memory challenges, mnemonics and things like that. But for a class like this, the way you're going to memorize it is by doing problems. Narayanan Sundrayajan says, what am I doing? What's my purpose learning quantum mechanics? So if you're just tuning in and you're not sure what I'm up to, check out the first video in this playlist where I explain the whole project, and we're kind of in the middle of things. So that would probably be easiest if you're not sure what's going on here. Okay, So I am going to get back to working on this 6.5a. And I remember, where do we have the, let's get over here. Okay. So, okay, all right. So this one here, I was trying to remember because what I had done is we have to have the matching conditions at the boundaries. Now, unlike the square well, there are no harmonic wave functions anywhere here. We just have one decaying growing exponential, one decaying. I think this would be a growing exponential. And this is also growing exponential. I think that's what we worked out. Yes. Because this is going to, when it's negative, it's going to be going back. And then we're going to start turning away again. So I think this is the solution that we have here. But the key here is in the last problems, there was a matching condition on the first derivative. So the first derivatives also equal each other at the boundaries. But here we have delta functions. So of course they are shifted by a delta function. So this the first derivatives of these, which is going to be, this is minus beta cx, and this is going to be equal to this change in potential, which is some function of this omega naught. So I'm trying to remember exactly how this works because it was not, I think what I did last time is I just put W naught here, which is the voltage, but that's wrong. I don't think it's the right units first, because this is a energy. I think this is an energy. Energy over length. And these are going to be the actual psi function. So these should be 1 over length squared. So we're wrong units here for this, but it's going to be proportional to that because that's how strong the potential is. Now I'm trying to remember. If I can't remember, I will look at my notes because I do remember writing this down, but it's always good to try to see if you can remember. And the way to do it was there was an integral. So basically we want to go from negative epsilon to epsilon, and we're going to take the limit as epsilon goes to 0. And I think we're doing this over the Schrodinger equation, because we have to find the thing that matches the Schrodinger equation. So I think we want to do E hat psi dx, and then this would be limit as epsilon goes to 0 of epsilon to epsilon. And then we have, this is going to be, is it minus IH bar squared? What was it? No, this is not, this is, yes, H bar squared. H bar squared minus 2m d, oops. I'll just put sine double prime x. And then this is going to be plus, and then this is this W naught delta of x. Right. And then I think do we want to have the DET on the other side? So we're going to have equal to, let's do lim. So it goes to 0. Let's do the whole equation here. This is I h bar DET psi, but because this is just going to be E psi, because we're dealing with an energy eigenstate. Okay. Let me rewrite that here. This is 2m. Then we have plus this is just going to be 0, because when we take the limit at here, they're going to just be the same. Right? And then is this going to just be equal to E psi is equal to dx. This is just going to be 1 times this, so we're going to have is equal to oops. No, I need to get the first derivative condition here. What am I missing? I need to take the derivative, I think, of this. So if we take the derivative, I think we're still going to get the same thing, right? I guess these are wells, so I should put a minus sign here. I'm definitely forgetting something. Oh, right. So this is going to be equal to, I'm skipping over something here. E psi is equal to limit as epsilon goes to 0 of psi of epsilon. It's gonna be I think we want to do the same thing on this side too, though. Right? Yeah. So as this goes to 0, this just becomes the difference. I'm still where I am before. Okay, let's look at what I did for this question last time. It was so it was from squared. So this is the answer. How do we get this? Let's get the Schrodinger equation out. We have E phi is equal to r squared over 2m phi double prime minus, I think, or formula sheet. Yeah. phi. So we may subtract those guys out. And we have h bar squared over 2m phi double prime is equal to phi. Now we're going to do this. And here we're going to get phi prime of this e is going to get dropped out. Have this like this. Phi, and we have minus e. E phi. This is going to be 0 because it's going to be the same on both sides. And this one is just going to be the function. So we're going to have so this is so change in first derivative is going to be equal to this as well. This is going to be just 1, I think. Because we know that it's smooth here. So this is 2m h bar squared w naught. And according to the solution I just looked at, which unfortunately I kind of looked at, I assumed I could cross off the odd solutions, but that is not the case. So I'm forced to deal with it in full. So we have our And we have e to the alpha x, c to the alpha x. So the simplifying idea is that this is all alpha. And why is it all alpha? I guess because the energy gap, so the difference between the eigenstate energy in this is constant throughout, so it has to be the same here as it is here. Okay. Like we don't get to pick that. So so let's try to see if I can do it with those hints. D to the minus alpha x. This is going to be at minus L, it's going to be at L, and then we're going to have first derivative condition is going to be and this one is going to be at minus L, it's going to be at L. So let's substitute in. So we're going to have A e to the alpha L is equal to B e to the alpha L plus e to the minus alpha L minus, this is minus L, so I got to do minus, minus, and plus, and then this is C e to the minus alpha, or D e to the minus alpha L is equal to B for equations, for unknowns. I think this is what we want to solve. So if we get A here, plop it in here, it's going to cancel. So let's just, I'll write it all out. A is equal to L, and so we have sec. I'll just copy this over here. And if I look carefully, this can cancel this. I'm going to get two of these, so we're going to have, there's an alpha there, right? Yeah, alpha. We're going to have 2 alpha C e to the alpha L 2m over jar. I'm going to have the same problem I had last time. The even and odd solutions separately. Yeah, let's separate it up. Oh, it's gotten quite dark in here. Let me just turn on this light. So let's do even first. Even solution. Can I do even odd like that? Yeah, don't know that I can. You know, let's just leave it. Let's just leave it right here and see how it works out. So C is therefore equal to m over h bar squared w naught. And this is e to the alpha. It's our C. So which ones have we used so far? We used this one and we used this one. Let's plug this guy into here. So let's get D in terms of these guys. So D is going to be the same thing as A was pretty much B to the alpha. And then let's substitute this one into the top equation. We're going to have minus alpha. And then let's get e to the alpha L plus minus alpha L. And then we're going to have minus alpha b e to the alpha L. Right. Plus alpha okay, same thing as last time, except these guys are going to cancel, and we're going to get b is equal to give me m over e to the alpha L. So we've used, can we put it all together? Okay, so it's like e to the alpha e to the alpha L. Is that right? Yeah. Oh, looks like it is right. So this is not actually, this isn't going to be e to the, oh, this is e to the alpha L divided by, what else? This is e to the minus 2 alpha L. And then, and then these ones should cancel because C is, yeah, C's match. So A is going to be equal to, oh, this is giving me the same mess I had last time. So let's try putting this back into this equation here. We have alpha Oh, I guess I can merge these. 3 alpha L. So I can just go like this, 3 alpha L plus e to the minus alpha L. E to the minus alpha L. So this is going to be minus 2 and 4. 4, and this is going to be 2. And then that's going to be equal to, it's our B. It's not equal, this is minus alpha, and then B is B minus alpha L. B to the minus alpha L. Yeah, so that's going to be e to the minus 2 alpha L, and then this is minus m alpha h bar squared again W naught. And then for our last one, it does cancel, so I have minus alpha, no, plus alpha. And then this is all equal to 2m W naught over h bar squared. So we should be able to do some canceling here. So we can pull all these guys out here because they're multiplying every factor and just get m W naught over h bar squared, right? So we divide by this on both sides. We just have 2. And so we have alpha e to the minus 2 alpha L. This is plus alpha is equal to 2. And then this guy and this guy is going to cancel. I have alpha e to the minus 4 alpha L plus alpha equal to 2. So Matthias is asking, do I have any physics course? Do I have any resources to recommend? Well, it really depends on what you're trying to learn. I mean, materials are useful, but the main thing you want to be doing is practice. So it's really depends on the class and what you're trying to learn and how you're accomplishing it. I don't think there's any general purpose physics resources I can give. Obviously, I think MIT OpenCourseWare is pretty good. I think Khan Academy are pretty good. I think these are all pretty good resources. But again, physics is too broad. It really depends on what you want to learn. So this is alpha is equal to, yikes. E to the minus 4 alpha L plus 1. Well, I didn't really end up where I wanted to go here, did I? It's kind of what I had last time, although it is simpler. It isn't quite so messy as last time, but Well, let's look at the solution they have and check over that, but I might want to try this one more time later. Where are we here? Problem 6. What is it? 6, 5? 6, 5. Oh boy. So we did do even odd solutions. And what did they do here? We have psi even is equal to, we've got a e to the, I'm going to continue to use alpha here. We had b hyperbolic cosine alpha x. And this is also a e to the minus alpha x. Okay. So cosine h, I believe, this is going to be e to the alpha x plus e to the minus alpha x. Is that right? Let me just check. Let's look it up on Wikipedia. Okay, you know what? I'm going to make, this is a good place to list some of these facts. So where is a piece of paper I can write these down? Because I was going to do some of these hyperbolic trig functions as flashcards, and you know, now is a good time to do it. Unfortunately, I'd made more of these flashcards and I spilled water on them and they got all wet. How many times did I fold this? What I did was something like this. Yeah. So that's roughly that. I'm just going to memorize some things with these hyperbolic ones because I think I know most of the standard sines and cosines, but the hyperbolic ones I don't think I've ever used them before for anything, and so they're just a little unfamiliar for me, and that's making it harder for me to remember them. So I'm going to make maybe like, this is going to be 8. I might make some more, just so that I can, you know, memorize them. It might be useful for the exam, and if not, I mean, it's still good to get familiar with these. Obviously, you at home, if you're going to do something like this, you can buy actual index cards. I just have not bought any, so I'm not going to waste time trying to get exactly the right materials here. All right. And I have to remind myself to do some of these flashcards at the start of each session. I was going to do some, and then I got distracted and started working on problems right away. It only takes about like 2 minutes to do the flashcards, so I just have to make sure I do them often enough to actually learn them. Oh, here we go. Okay, so I got 8 more guys here. Let's start with Q. You know, maybe I'll rewrite this. It's a little bit easier to see. I'm kind of smudging it here. All right, and then I had the blue pen for my answers. This one's equal to e to the x. This is e to the alpha x. plus e to the minus alpha. Oh, I gotta put kappa x divided by 2. Also, I'm just going to put also e to the 2 kappa x plus 1 over 2 e to the kappa x and 1 plus e to the minus 2 kappa x. Put those as little asides here. All right, 1 down. Add that to the list. Now let's do sine. Express sine h. All right. And let's go sine h kappa x equal to kappa x minus kappa x by 2. Also e to the 2 kappa x minus 1 over 2 kappa x and 1 minus x divided by 2 times e to the minus x. All right. Okay. Add that to the list, and let's just do 10. Noah's asking, am I doing anything to push them into long-term memory? No, this is just short-term. I mean, you might say that that's kind of self-defeating. Why do that? But my goal here is to learn this information for a particular period of time. My overarching goal is to get kind of an intuition of quantum mechanics. So memorizing these things and making sure that they're at the tip of my fingertips is not super important to me. If I were trying to do that, I would use an SRS. I have done that. I just find that I tend not to work on maintaining things that I'm not actively using, just because I just find it gets to be pretty big, the SRS that you're doing all the time. But I mean, that's a personal choice. All right, so I did 10 each, and then the answer is going to be this is e to the kappa x minus e to the kappa x over e to the kappa x plus minus kappa x. I'm going to put also minus 1 over plus 1. All right. Now, I think I want to include some derivatives as well. Let's go. I'm not going to use any of these. I think cosine, sine. Let's go. Oh, good. Okay, so this would be another one. Express. I might just do one of these. Is equal to I sine. Also all right, and let's get derivatives are what you'd expect. So I don't know whether I'll just put the derivative because I wasn't sure on it. So what did I do? Cosine? Yeah, signage. Note dx dx sine hx minus sine. Okay. And while I'm making flashcards, I might as well just get these. I'll do some with the. Let's go Gaussian integral on Wikipedia. So let me go here and see if I have the full one. I think. Okay. to the negative x squared over a squared dx. And so that is going to be equal to so it should be a root pi, I think. Yeah, a root pi. Because if we have a up here, that should be right. Okay, let's see if we have the higher order ones. All right. Do we have the higher order polynomials? Gaussian function. Where is our polynomials? How do we do it with just x? Oh, I think this is 0. Yeah, this is 0, right? Because it looks like all right, and then I'll do one more. All right, this is going to be double factorized, so I just want 1. So 2 minus 1 double factorized is 1. Then a 2n plus 1. Hold on a sec. of x squared e to the minus x squared over a squared dx is equal to root pi divided by 4, so it's just going to be divided by 2, and that's just going to be a cubed. Is 1 a cubed divided by 2, I think. And I think that's as high as I want to go. I doubt I'm going to need to know more than this one. All right, so I've made some new flashcards here. How many do I have? I'm just going to shuffle them up a little bit. So one of the people are asking me, like, why not put this into a space repetition system so I can memorize it forever? And that is a good question. It is a little bit of a personal choice. I tend not to do space repetition just forever, holding everything in memory. I found that to be a little bit cumbersome after a while. And the reason why is just because I have, like, probably from over my lifetime using SRS, I have maybe like 20,000 flashcards. And so to maintain all those in memory is quite a bit of work. And so what I tend to do is I tend to let even just usage dictate how long I remember things. And I don't mind relearning stuff. I don't mind getting myself to relearn stuff, especially stuff like this, because stuff like this is like, oh, I forgot what are these derivatives. You can look it up, which I'm doing. So my approach tends to be to use it and lose it. But I do have, what was I going to say? I do have these flashcards because I want to have them memorized in this period of time that I'm trying to actually work on these problems. But long term, I don't think I'm going to try to maintain them. It's just a little bit not really what I'm after for this. But I think that's also okay, is to learn some things for a particular context, perform well in that context, and then be okay with letting them atrophy if they do. Because if I forget what these are, it probably just means that, you know, they weren't that important to me, or they weren't that relevant to the things that I'm working on. So I'm going to leave them kind of just out there, but I will keep the flashcards around. But yeah, I don't think I'm going to use the space repetition system. So getting back to this, so that was a little bit of a detour. I'm going to go and look at this right here. So I think this is kind of interesting that we have A, B, and so we only have 2 variables here for these even and odd solutions. 2 for this. So let's see if I can solve it with this simplification, because I think this is something that I was kind of forgetting. I thought that there was, see, I'm trying to do them all together and it just makes a mess. So let's see if I can do that. So we have A e to the alpha x is equal to B parabolic cosine of alpha x. And we have A e to the minus alpha x equals E cosine h alpha x. And this is at minus L, this is at L. And then what do we have? We have the first order derivative, so it's going to be alpha A e to the alpha x. Derivative of this is just sine, so we're going to have alpha B sine h alpha x. I'm just going to do that just so that things don't get messy accidentally. plus our 2m omega naught over h bar squared. And then we're going to have the same thing over here. All right, and this is again at L, and this is at minus L, and this is at L. So let's plug in the L's. So now I have A e to the alpha L is equal to B cosine, hyperbolic cosine of alpha L. And I have A e to the minus alpha L. So this is just going to be, this one had a minus, so minus, and this is minus alpha L is equal to B cosine H alpha L. And then we have alpha A e to the minus alpha L. And this is going to be minus alpha to the alpha L is equal to alpha B sine H alpha L plus 2m naught H bar squared. All right. So this is trivially true. So I think we can just scratch this because cosine H is even. So this is just the same. This is just trivially true. So we can just eliminate one of these functions, which I mean makes sense. We only have two unknowns, or three unknowns, I guess. So let's plug this guy in here. So A is going to be equal to B cosine H over this. So let's just plug it in here. I'll do this one. E to the minus alpha L. And then this is e to the minus alpha L. Minus alpha L plus W naught over H bar squared. So let's divide out by alpha and cosine of H. So we're going to have B is equal to, now I have to be careful because this doesn't have a B in it. So B of cosine H L minus sine H minus alpha L right? Now this is an odd function, so we can go plus cosine H plus sine H. That's a good identity to know. I think let's just represent those as exponentials. Let's go. Let me just write B alpha. And let's go. This is going to be e to the e to the alpha L plus e to the minus alpha L by 2 plus e to the alpha L minus e to the is alpha L over 2. So this is going to cancel here. And we're going to get B equal to 2mw naught h bar squared. Alpha h bar squared. This could be 4. Add the 2. And then this is going to be e to the alpha L. Is that right? Because this is, oh no, this is just going to be 2. Hold on a second. E size divided by 2 is just 1. So this just becomes e to the alpha L. So we're going to get alpha e to the L. Yeah, okay. And so where's a function we can put this guy in? Let's plug it into our last remaining function. So we have minus alpha. What was our A? Our A was equal to so that canceled there. We had B cosine H and the B cosine H alpha L. Alpha and the B 2mw naught for alpha h bar squared e to the alpha L. Plus oh, all right. Making progress. So I think we can factor out this, right? I think so. So let's go gadoosh, gadoosh, gadoosh. Now we have minus alpha line h divided by alpha e alpha l. These guys are also going to cancel. And we're going to have alpha sine h alpha l. Oh, these are also going to cancel here. Over e to the alpha l plus 1. Okay. To multiply everything by e to the alpha l of e to the alpha l. Let's turn these back into exponentials. So this will be e to the alpha l plus e to the minus alpha l minus, and this could be 2 times e to the alpha l. The sine h plus e to the alpha l minus e alpha l. All right. So this guy's going to cancel to 1/2. So we're going to have minus 1/2. And then this is going to be minus 1/2 e to the minus 2 alpha l. And we have this again, it's going to be 1/2. And we're going to have minus 1/2 e to the minus alpha l. All right. Maybe let's just If we multiply everything by 2, let's move this guy over, and this is going to be 1. And so we have plus 2. And then that's going to be 4. So we have well, this can't be right. Oh my god. I made a mistake somewhere. Minus sign or... Oh boy. All right. I'm going to go through their result because these linear equations are really tedious, and I'm making algebraic errors which are screwing them up. So, to, no, you're not, h bar squared k minus 1. Yeah, I did something here. Maybe I didn't use the equation twice. All right. Oh. And all right, well, I might be making a mistake there, but I think it's just probably best to move on at this point. So I'm gonna cross these guys through right now. And A and E, what was E? Oh, right, this is A. Jeez, I'm only got on A. All right, E. What would be the force? Oh, right, this is the, okay. So force is equal to, well, energy is equal to force times distance. So dE dt is equal to force. And so what is our energies here? We want to have not ddt, oops, dx. And we're trying to vary the distance between L, so I guess maybe more appropriate, this should be ddL. And then what's the right way to do that from here? Let me just copy this over here. Yeah, so let's focus on our even state here. Our so if we have E, and we want to go what do we have? So this E was, E is unaffected. Oh no, KL. So this is going to be equal to K plus This is going to be K tan H. I'll do KL just because it's going to be confusing otherwise. KL plus this is going to be, this is cosine H. Sine over cosine. What am I doing? Sine. DDL. And our G naught was what? ML W naught over H bar squared. DL is just 2M W naught over H bar squared. So we have K plus K about 10 H K L. K is going to come out here. Oh, I need quotient rule. I think it's going to be what? Quotient rule is oh, good thing to check up the quotient rule. I've not used the quotient rule in ages. Right. Okay. So it is going to be cosine K cosine H K L sine H K L minus K sine H minus sine H. Cosine H. This is, hold on a second. This is also cosine H. All divided by all right, so we have K and so this is 1 minus tan H squared KL is equal to 2M W naught over H bar squared. Ooh. Well, this would be the force, some transcendental equation for the force. What are they asking exactly? Best done numerically. So I'm not going to do this numerically, but let's just see if we got the right thing here. We want E. Okay, well, I didn't solve it, but it's a transcendental equation, so I wouldn't be able to anyways without using numbers. All right. So I'm going to make a special note for add that up there. No, I'm at 6.6 GI. So this is a pretty specific one. Mm-mm, 6.6 GI. All right. Suppose Kj, where S is a real quantity and K is Hermitian, is J Hermitian. Okay. So we have K and J is equal to minus Sj. And K bar dagger, I guess, is equal to K. Does J dagger equal J? All right. That's the idea, right? So let's apply this to a function. So we have K, J, commutator times, let's see, F of G. So I think we can do both of these. We can separate them out. And we have minus. So if we commute it through, we'll get minus Sj, so we get I'll go like this. It's always helpful to write it out, so I can go jk minus jk. And this is going to give us our minus Sj, so it's going to give us now that it's right next to the f and we know the k is formation, we have minus Sj plus j f. Is that helpful? Let me try it again here. How can we push this through? So got this is what I was trying. I'm going to drop the hats because it's going to be annoying otherwise. Now, if then j f g is equal to f j g, right? That's the definition of hermeticity, right? No. G. No. Yeah, that's right. So let's work it through again. We've got our kj minus jk. Now one of these guys can just come right through. So we have, I'll split these apart. Kj, just need one bracket. Kjfg minus jkfg. And I think this is the one that we need to get over. So this guy is just equal to JF KG. And this guy, we have the, we're going to add the commutator in here. So we're going to have our minus. I'll just do it again. JK minus JK plus KJF. And then this is the K and J commutator plus JK. So we have, I don't think I need to do this. I don't think I need to do that. So this is going to be minus SJ plus JK. So if we go minus SJ well, this doesn't really help us. This is just already true. I need to do an equality with J and J hat. But I don't know the commutation relation with that for sure. So basically what I'm trying to do is show if we have J, F, and G, and if J is J hat, then that should be equivalent to J of G hat. This is a I wrote it down up there. This is the thing we're trying to show. So let's work on this side now. Let's try doing the commutator on both sides. Right? We don't know what it is for J bar. What if we multiplied each of these by k minus k, and this by k minus k? This is just 0 now. Can't multiply by 0, I have to multiply by 1. If I multiply by k minus k plus 1. And I commute one of them through, and we get kj minus jk minus js minus sj plus j. Right? But now we've got this, which is the commutator relation, so we've got another one of those, right? So to convert this one, so we have kj. Did I do this right? Kj minus k minus plus jk. And then this becomes this becomes plus jk. No. No. Wait a minute. We had a minus here already. Yeah, but then it's minus, which is plus, so these cancel. Which they should, because I mean we just added 1, so what am I expecting? We have what? This is AB is now reverse BA. So we're going to have JK minus KJ G. So my guess is no, it's not Hermitian because plus Sj minus Sj, you're not equal. So if J were Hermitian, equals right, but we have plus so it can't be. Assuming the answer is no. Which question was this? 6GI. Oh, okay, yeah. I don't know why I was under the assumption that it was Hermitian, and that's why I'm spending so much time trying to show that it is. Okay. Problem solved. So that was the last one for problem set 6. And now I'm going to do 7.3 B and C. Seven point three B and C. Oh, geez. Okay, these are not trivial problems. Goody. Maybe I'll take a little flashcard break right now. Do a few flashcards. Okay. You guys see the flashcards? I'll make sure I put them so you guys can see them. So dimensions of size 1/√L, or 1/√ meters. Express the E operator in terms of this. This is going to be H bar omega, A raise A lowering. So A plus A minus plus 1/2. So it's going to be H bar omega, A plus A minus plus 1/2. Yes, sine. In terms of sine, oh, this is I don't remember what this is. How do I express this in terms of sine? Oh, it's I sine I kx. Minus I sine I kx. I sine I kx. Minus I sine I kx. Okay. Tan each is exponentials. So that is e to the kx plus e to the kx over e to the kx. No, e to the kx minus e to the minus kx over e to the plus kx plus e to the minus kx. So each k as exponentials, that is e to the kx minus e to the minus kx all over 2. We also have these ones there as useful. Cosine, hyperbolic cosine is same thing, but plus, what is G naught? It is M So it's L over root mv all over h bar squared. Let me think. No, the h bar is in a root, so it's going to be mv over h bar. And there might be a 2 here. No. H bar is outside of this. Why is that again? Oh, right. These also the kilogram term. Okay, I got that one wrong. Sine h. LZ in spherical chords is IH bar DD5. Yeah. This guy, oh, it is what is this? X squared over, what is this? A cubed divided by 2 times root pi. Yep. Units of h bar is kilograms squared, meters squared per second. Oh, kilograms times meters squared per second. Okay. What is the wavelength in terms of MV? Well, P equals h bar k. K is equal to lambda over 2 pi. So 2 pi times 2 pi mv over h bar. 2 pi h bar over mv. P is 2 pi. It was 2 pi over lambda. Okay, just remember that k is 2 pi over lambda, not 2 pi times lambda, or lambda over 2 pi, right? Yeah, I think so. Okay. L squared, this is L times L plus 1 YLM. H bar squared. Gotta remember those H bars. Oops. Let's make sure I flip these over. And then this is LZ YLM is going to be H bar M YLM. I should put the YLM here. Did I have the... All right. This guy is A root pi. And this guy is 0. Right. So let me just shuffle these guys up. I can do some more tomorrow. All right. Put these guys back over here. All right, let's get back to questions. Little flashcard break. I'm going to just get a little bit of water. And it's that time of day where the light cuts right through my face, so enjoy that. All right. 7 BC. Problem set 7, 3. Oh, okay, here we go. All right, given by this ugly, awful thing. All right. So let's start with our G naught equal to 20 case. So this is a graphing problem. This is a barrier. So what do I want to put in each one? We want to have T in terms of E naught over V. So let's go up here. So this is lower than the barrier, and this is higher than the barrier. And G naught is very high, and G naught, in case I just forgot, is L root M V over H bar, and this is, there's a 2 in here, just for convenience. So let's get, this will be transmission probability 1. So let's remind ourselves what our function is. It is, so let's look at the this case first. So let's re-express everything in terms of these dimensionless variables. So I'm just going to do that up here because I don't want to save, I don't want to waste paper, and I already drew my graph and I don't want to be switching back and forth. So in terms of E over V. Oh, right. What was the right way to do this? So we're just going to divide all the energies by V naught. That was the key. So this is going to be T E less than V is equal to, it's going to be 1 over, we're going to have 1 plus, well, V over V squared is going to be 1, and this is going to be 4 E over V, and then 1 minus E over V sine H, and then the alpha is, maybe I'll just write it as sine H squared alpha L. And I'm just gonna put alpha star with alpha star equal to 2m over h bar squared. Oh, we want to translate it to G naught, so hold on a sec. 2m over h bar squared. E over v minus 1. And how do we compare this to g naught? G naught is I want to express alpha in terms of G naught. Oh, wait, hold on a sec. We've got a different formula. We got G naught. Oh, this is G naught squared. L squared. So 2m over h bar squared. So how do we convert alpha into G naught? So we can go alpha star is equal to G naught squared over L squared. And now we have V, so this is going to be let's go with our old equation first before we substitute it in. We had V minus E. I think it was V minus E. V minus E. And we had now divided by V. So this is 1 minus E over V. And so G naught is going to be alpha L squared. So we can just put this in. So this is going to be G naught over L of 1 minus E over V. And then our TE greater than V, we're going to have basically the same thing, plus 1 over 4 E over V. And this is E over V minus 1. And this is sine squared. And I think it's going to be about the same thing, yeah. G naught squared over L E over V minus 1. Okay, so that's quite small, but we've got our thing here. So what's happening here with this? Well, this ratio is less than 1 when it is equal to 1. What happens? So E over V, let's say that is equal to 1. We have 1 minus 1. So this is 0 over 1. So this goes up to infinity. But this one here, what does this do? We have 0. What is sine h squared of 0? That would be e to the minus. This is also 0. This is 0 and this is 0. And I think this one dwarfs this, right? Let's look at this case. So I think we're still here, right? And as this is less, let's just plot, go Wolfram. Plot sine h. So this is going to rapidly increase. And this is going to be less than 1. So I think we're going to have something like and then this is what's changing here. Sine squared. So where are the periods of this? Minus 1, 0, and then if it's a little bit more than 1, a little bit more sine squared. This is going to be a little bit higher. but it's going to be, is it stretching out? Because we got this plus this thing. This is becoming a smaller contribution each time. This is going to be something like that, right? Now, how low does it go? That's a good question. The lowest it's going to go is going to be when this contribution is all equal to 1. And when does that happen? This is 1 when we have well, it has to be at the 90-degree mark. So this whole thing has to be pi by 4, pi by 2. And if this is pi by 2, g naught squared over L. So this one is g naught squared is going to be 400. 400 over L EV minus I don't know that I can calculate this exactly. In any case, this is going to be 1, and the EV is going to be some number. Relatively small because we've got a huge frequency thing. So EV is just slightly more than 1. So just slightly more than 1 is going to be point something pretty insignificant. And so it'd be like 1 point something small, 10 point something small. This should be fairly large, right? This is going to be 1. All right, we have our 1 over 4, and then this is going to be, let's just say it's something small. So it's just like 1.001, and this is going to be 0.001. This is going to be like 4,000. So it's going to be quite deep, right? Transmission probably is going to go off quite sharply. So if this is high, then it should probably be more like this. And then what happens when we go up 1? So let's try it again at, what was this? G equals 2. So this is going to be not so steep. And then this is going to be somewhat longer. And then what's happening? So the period of this thing is going to be stretched out. Plus, it's also going to be not quite so large when we do it. So it's going to be more like, I'll do it a bit more than this just to get a bit more exaggeration here. And then for G naught is equal to 0.2 and just like the most gradual maxima are very close, I think. And question C, how does T vary with L? And this is going to be E naught, S and B naught. This is going to be this sine H term, right? So it's going to be 1 plus 1 over this sine H term. So it's going to rapidly go down to 0. So as L is increasing, it's G naught over L, right? As L is increasing, this is going to become exponentially smaller, which is going to make, right? It's like that. Okay, let's look at these and see whether I'm sort of right. 0.3 BC. So 1, 2, 3. I did that wrong. So hold on a sec. I did G naught squared over L. So we're going to have G naught root this and G naught root this. Oh, geez. It's mostly right, I think. Medium barrier. A thin barrier. So I think this is the one that I thought that it wouldn't be curved that way, but I guess it is. Okay. So I think other than that, no mistake. I think that that's okay. So I'm going to cross this one off. 7.4C. C. Oh, use the unitarity of S. S to show right, unitarity means that U dagger U equal to 1. I think that's unitarity. Let me just confirm here. I think we did this earlier in this problem set, which is why. Yeah. Okay. So 7.4C. And our S matrix is equal to R T T R. Unitary to show that. So that's saying that S bar S is equal to 1 is equal to so this is what is the complex conjugate? Oh, right. This is, I think, the difficulty I had, which is why I wanted to do this. What is the complex conjugate of a matrix? Or what is the adjoint of a matrix? Generally, do I have it here anywhere? What's the adjoint of a matrix? I'm pretty sure. I'm pretty sure this is. Well, we can just work it out by this unitarity of here. So let's do the problem the opposite way. So this is going to be our r squared. First row, first column, r. And this is going to be our t, and then first row, second column. I think this is right. Shouldn't matter which way I do it. All right. So this has to be r squared plus t squared. This is the wrong way. Maybe I'm doing them backwards. Maybe I am. So let's try. No, this isn't right. It needs to be r times r in the first row. This has to be 1. And then the second one is going to be so I think this is right, and then this we have, because of this we have r squared plus that's because this is 1, 1 of our matrix, and then same for this. This is by 2, 2, and we have r cross t, r t plus because this whole thing is to be equal to this identity matrix. Columns of S are orthogonal unit vectors physically. Why must this be true? Just because reflection and transmission amplitudes are independent for leftward and rightward, is that it? So unit, because need to preserve probability, and orthogonal. Why? What would it mean if they weren't orthogonal? I'm not sure why it's orthogonal. This is 7.4c. 7. Oh, there's no reason given. All right, well, I'll take it. And we're done one more. One more in 7.5 all. Geez, all right. Okay. All right, let's look at 7.5. I don't know whether I want to dig into it too much. Of an attractive delta function. Wow, great. Okay. All right, let's look at our system here. So we've got a scattering system, got a single delta function, and we want to know how much gets reflected. All right. So same idea as before. We're gonna have left-hand side, right-hand side, and except in both it's gonna be, we're scattering states now, so it's gonna be a sine and cosine. There's only gonna be one bound state, right? And it's gonna have to be even. Yeah, let's just do the e to the ix. So we have a e to the ikx plus b e to the minus ikx. But these are invariably coming in from the right, going out from the right. Let's go c e to the ix plus b, d e to the minus ikx. And we're going to send from, if we're going this way, so we're going to have this one, we're going to remove for that reason. And this becomes our so we have a e I k x to c e to the I k x, and divide everything by a e to the I k x plus b over a is going to be our reflected coefficient, our reflected e to the minus I k x. Right? And we also need our derivative conditions. So this is our only derivative condition is what we want. This is going to be minus what do we have on this side? And we have our what is it for this potential here? It's not V naught. I worked this one out already. We're going to have it's 2m V naught over h bar squared, I believe. Right? Yeah, I think it's that. Okay. Okay, I think I'm going to put a pause in this right now. Just a reminder of myself. Oh. Okay. So it's nearly the end of the studying session that I was going to put in for this afternoon. Jeremy asked if I've ever done a course in normal pace. Well, yeah, of course I have. I mean, I did a whole university degree and I did them in the normal pace. I didn't do it. Why am I doing it this way? Well, I mean, it is arbitrary. I could have done this spread out over a long period of time. So I could have, done this over, say, 6 months or a year. The reason for doing this particular one is because I had a gap in my schedule and I wanted to spend month doing a project. I'm not often learning like this. I'm often learning when I have, just putting in, half an hour a day on this or half an hour a day on that. I think there's some advantages and disadvantages to doing it this way. The disadvantage is that when you crunch up the time, it does impact long-term memory somewhat. The advantage I find is that it's often easier to make progress if you have a shorter period of time, it's a little bit easier to maintain focus and motivation. So I don't know, for this one here, this was the period of time I had. So this is how I decided to do it. I think also it's a little bit easier for me when I have it over this time period to kind of schedule it, get it in. I might do some classes that are just going to be like an hour a day for a while, but this is kind of what I did during the MIT challenge. I also think it's kind of useful for me to show this in this pace as well, because some of the things students struggle with is often how do you focus for periods of time, or what should you be doing if you don't have much time to study. So that's also part of the reason that I like doing it this way. But I mean, it is arbitrary. I could have done the exact same types of things, but spread out over a longer period of time. I haven't totaled up the total number of hours I've put into this project so far, but once I get a sense of the hours, that hour amount is roughly what you could expect for total difficulty. Go through a calculus course. Well, I've already done a calculus course, so I don't know. It's hard to say because I'm thinking back to when I had to do it. If I were to do this course, well, I mean, you can just look at the playlist of videos I have and just tally up the hours. I might do that later to figure out how many hours I put in the total thing. So I don't think that if you do it over an hour every day, it's going to have two trade-offs. I think you're going to probably have a little bit of forgetting in between each session, not a ton, but a little bit of forgetting in between each session. So it may take you slightly longer in terms of total hours, but the trade-off of that is you probably have longer retention over a longer period of time too. So I think hour a day, it's probably going to be a wash. I don't think it's going to be a huge difference. Noah's asking, how hard do you think it would be to get a programming job, I'm assuming? I am also a self-taught software developer. When I was not self-employed, it was not that hard, but it was also a time when most devs were self. I didn't get a job offer. I did get offered to interview at places. I just didn't pursue it. And part of the reason was that I could have tried to make a point of seeing if I could have gotten a job after, but I didn't really feel like applying for jobs if I wasn't actually interested in working in any of those places. And that wasn't what I wanted to do. I didn't want to work there. I have talked to a lot of people that have different undergrads and ended up getting dev jobs. So for me, for instance, it would be also different because I do have a bachelor, just not in computer science. So I think if you have a bachelor, which shows you're kind of college educated, I know it's a whole signaling game, but then even if you don't have the background material, if you can demonstrate that you can do those things, I think you might suffer if you are in sending your resumes to a pile where they might ignore people that don't have the background. But I mean, most people I know that get jobs, the resume pile is not really where you want to be when you're applying, period. You kind of want to have someone who knows about you and they can refer you because they recommend you and stuff. And that's an unfortunate part of getting a job, but I think that is important. Yeah. So do I ever find what I'm doing extremely boring? Bored. I mean, sometimes I get bored. I think for this, I don't think I find it boring. I think I find it very challenging. And so in some ways, that's the opposite of boring. I think I want to be careful about what we use when we use words, because people describe boring in a lot of ways. Oh, this is so boring. But sometimes, there are stuff that I'm doing here that I find tedious. So I guess you could say that's synonymous with boring. Like this stuff here that I'm doing where I'm having to solve these linear equations and moving stuff around, that can be a little tedious. But I mean, yeah, I don't know. I guess it just depends on what you're learning and what you feel like. There's definitely been subjects I remember taking which I find uninteresting. I think for me, they tend to be, boring. I tend to find is synonymous with this is kind of trivial or easy. Another way you could put it is boring is synonymous with unimportant or something that I don't care about. So those are two kind of different senses of which something can be boring. One, because it's too easy, it's trivial, or tedious, and it's just a lot of work, but there's nothing interesting about it. And then the other way something could be boring is if you don't find it important and interesting. And those two problems tend not to happen when I'm doing projects like this, because the first case, if it's too easy, I have control over the challenge level. So if it's too easy, I can go a lot faster, or I can, obviously this is very challenging, so I'm not in that situation. And then the second situation is where you find something uninteresting. But I mean, if you didn't find it, if you had no reason for learning it, you wouldn't be here in the first place. So I tend to pick things that, I do have some interest in learning from the beginning. I mean, for me, I'm very interested. I don't often think about, I guess I'll put it this way. Some of the stuff I find interesting from just an intrinsic standpoint, meaning that, this problem interests me because I think the conclusion is interesting, or I think that there's some kind of interest to it. For other things, I think what interests me is the intellectual challenge of it. And so I think that's why I kind of translate it all down to challenge level, of finding that right challenge level for it. Because I mean, you can give someone a Sudoku puzzle, and I mean, Sudoku is not it's numbers, it's not interesting. But if it's the right challenge level and you're trying to figure it out, it can be quite entertaining. And I think the same thing with video games. I mean, the same idea that if the game is the right challenge level, you find it very engaging, even if there's Like there's nothing important about it. So yeah, not important plus uninteresting, but it's part of your course. Yeah, I mean, this was something that I definitely felt in some of my when I was actually taking classes in university. That sometimes it felt, boring and interesting. I mean, you need some more discipline to get through it. That's one of the advantages, I think, of this, because you have some flexibility of how you choose these projects in the first place. You don't so much get into these situations where you find something, super boring, because I wouldn't have set aside all this time to learn it if I didn't think that this was something I really wanted to learn. One advantage to being self-taught is no economics courses. Well, I mean, I don't know what you mean there. Like I did economics courses during the MIT challenge because I couldn't fill out the humanities requirements, so I did economics courses. I really like economics. I don't know. I think both physics and economics are somewhat tangential to computer science. They're both just different systems of math. I don't know. Economics, I find the thinking that I learned in the economics classes, I find I use a lot more than, I would say, both physics and computer science for dealing with situations. Because economics is, a lot of it is a study of, how do people react to incentives? If you have some kind of system, what would you expect to come out of it? And so looking at kind of a lot of sociological phenomenon, people, this kind of thing, economics can be quite useful. Computer science is also useful, I think, in terms of decision making. I think it applies to a lot of cognitive science, and I mean, physics is everything, but you tend to be dealing with, like, it gets quickly complicated when you take it to systems that are physically complicated. So I think it tends to be physically simple systems that you are able to have that intuition about. I liked economics. I've always had an interest in economics. I did study business as in my undergrad, not economics. So it's a lot more like management, accounting, and finance and stuff. But I do find economics very interesting, and I would say a lot of people are dismissive of economics because it makes unrealistic assumptions. But having learned it, I feel like it's a lot better model for reality than people give it credit for. Would I consider computer science a science or math? I don't know whether I'm qualified to adjudicate that matter, but I would say it's math. I would say it's a branch of mathematics. I mean, a science, if I'm going off of my definition of a science, there would be some empiricism. For something to be a science, you go out, you do experiments, and you gather results. Very little of computer science is that. I mean, most of computer science is theoretical, that we have some abstract theoretical machine and we just do math to figure out what it can do. Whereas, like, you don't actually have to write the program to determine a lot of those things. I think there's some aspects of computer science that are similar to engineering. So software development, those kind of things are like engineering, which I guess you could say is sort of an applied science. So, I mean, how do you design a library that's going to be usable and maintainable and efficient stuff like that? There's some engineering components to it, but I don't think that I think I would describe most of the computer science I've learned as math and not science. You can do it with a pencil and paper. You don't really need to have like some kind of experimental apparatus. Machine learning might be a little bit of an exception, just because there's so much machine learning that is a kind of empirical. You have to just sort of try things out and set things up. But I don't know. That's maybe a little bit on the edge. What do I think of cognitive science? I think cognitive science is very interesting. It's cognitive science is generally thought of as an interdisciplinary field that combines philosophy, psychology, artificial intelligence, computer science. The kind of traditional way of it is just sort of how does thinking work? But I would say that it has kind of become the dominant paradigm for how does the brain work, or how does the mind work, or how do minds in general work. I think there's probably good critiques of some of the paradigms in cognitive science. So I know some people are anti-cognitive science because they dispute some of the fundamental premises. But I mean, it all just depends on what you mean by definitions. So I think, yeah, so cognitive science would include cognitive psychology, but it would also include artificial intelligence, philosophy. Trying to think if there's any other disciplines that would come in there. Maybe game theory. Yeah, cognitive science, to me, I think is just a very interesting field. I don't know whether we've progressed that much. I think um, reading more of the literature and things, I think there's just so much that we don't know and don't understand compared to what we do. I mean, there's a lot of things that people have figured out in terms of cognitive science, but whenever I read papers on cognitive science, I think that there's a lot of interesting ideas and theories, but not a lot of like concrete proof. How would I recommend self-learning a cognitive science major? So I'd actually considered that at one point. If you Google self-learning cognitive science, then this University of San Diego University of California at San Diego has a cognitive science department, and they put together a reading list for their graduate students who are going into it who had not taken it. And so I had this idea that I was going to go through all those books and do some kind of project. Now, going through some of them, I kind of realized that that wasn't really what I wanted to do. And so for my last book, I spent a lot of time reading about the issue of learning. So I'm kind of broken it down. That'd be kind of more on the learning end from a psychology end, whereas I would like to go a little bit more into machine learning, maybe more philosophy. Yeah, I also think enactivism is an interesting philosophy of cognition. I don't think it's as popular because I'm not sure what empirical predictions it makes. So like as a philosophy, I think it's quite interesting. But in terms of, well, what would this mean about minds? I think I don't know that yet. Like whenever I read books on enactivism, I feel like, well, what is this saying that, the mind is, doing? I just think that's the problem with enactivism, is that it's a little bit too nascent, that the people who are proponents of it haven't really worked the model into something that would offer some kind of empirical predictions different from kind of a cognitive paradigm. Do you still get as much shit as when you did the MIT challenge? Well, I don't know. I think that the MIT challenge, I got a lot of hate for that when I was doing it. And then after it was done, a lot of it went away. I think just because the kind of presumption of doing it, I try not to do challenges like that now, just because it's not really my personality. It was just kind of something that I thought was cool for that particular project. But I mean, I like to do things that are challenging, but I don't like to presume that, I'm going to be some great success at it. And I think that was part of the reason that it evoked that response. I think maybe, well, I don't know whether I would change it if I had to go back, but I think if I were to do the MIT challenge with my current stance towards doing projects, I would secretly hope I could finish in a year, just start doing it. And then when I finished in a year, I could say, oh, I did it in under a year, rather than declaring that from the start, because that's kind of arrogant. And honestly, it worked out well for me, but I mean, it could have been like this class where it was just way too hard and then I have egg on my face. What are the reactions in real life compared to online? I don't know. I mean, like, I don't really talk about it that much with people offline. I think people think it's interesting. I don't know. Everyone has different reactions about it. And a lot of, I think the online stuff is that, I'm overhearing conversations that people don't think I'm listening to. So sometimes people will be kind of snide or dismissive to me. But they're not as rude when I'm talking in person. When the Reddit post came up, there was a lot of kind of harsh comments, but then when I did Ask Me Anything, they were all pretty nice, just because people have opinions, but they're maybe not going to express them to my face. What does we have? Theory of cognition rise. Cognition, extended, embodied, inactive, embedded. Evolutionary computation. Do you mean like genetic algorithms? Is that what we're talking about? I mean, there's a lot of, I definitely think there's probably flaws with the cognitive model. I mean, there was a real revolution, I think, between the sort of symbolic approach and the connectionist approach, which I think was an important paradigm shift. That like pre, 1980s, there was a lot of like ideas about, well, maybe even before that, let's say like the 50s or 60s, there was a lot of ideas that, well, we know from Turing completeness that any kind of device can do anything as long as you give it enough time. So therefore, why don't we just pretend that it's some kind of serial computer and, just like abstract away the hardware implementation. But that obviously, now if we look at machine learning, we can see that the fact that it's massively parallel and the units are quite slow and it has this kind of properties implies like very different strengths and weaknesses as a computational device compared to a serial computer. And I think those things that were kind of dismissed as being unnecessary are actually really important when you're thinking about how does vision work, how does thinking work, how does all those things kind of work. Well, I mean, again, it's just I don't actually have a problem with people saying mean things about me. I mean, yeah, it hurts when I read them, but it's just like if you overheard your friends talking about you and saying, "Oh yeah, bad things about you." I mean, people have to have discussions about things when they're not talking about it. And I don't feel like anything I've done is beyond criticism. Like the MIT challenge definitely had its strengths and weaknesses. The all the projects I've done have had their kind of strengths and weaknesses. And so I used to kind of try to debate that, but I don't, I think it's just for, I just do what I want to do. And, people can discuss it and talk about it. So I mean, for the MIT challenge, there have been various kind of critiques and detractions. So like when people say, well, you didn't get a degree, or people will say, but you're doing all this coursework, why not try to actually focus on becoming a skilled programmer? Or what were some of the other things? I was too easy and self-grading my exams, or these kinds of things. And I mean, there's all some truth to it. Whenever a real person does a real project, there's always going to be things that are going to be bad about it or wrong about it, or not perfect. And so I just try to learn to not sweat over it and just do my best and do what I think is important. And if people don't like that, they don't like that. I guess that's how it is. Computation in studying the mind. Well, I definitely think if we're talking about just general Turing completeness, that the mind is definitely a type of computer. So I'm pretty convinced of that. That the computer is probably the best analogy. Now the question is how close does that analogy hold? So as I said, the kind of 1950s, people had the idea, well, it's all Turing complete. All machines that are Turing complete have a kind of general symmetry to them. So I think the brain is probably Turing complete in some, given the sense that a Turing computer has to be an infinite computer, but like some kind of limited version of that. But I think when we're dealing with the practical issues of how do you think, then we're not just dealing with Turing completeness. We're dealing with like what is the actual algorithm implemented, and there are things like what's the order of the operations, what's the actual algorithm, how does it work, strengths and weaknesses. I think that's actually really important. So that's sort of where we're moving. But I think it's just I think we're still a long way from implementing it. I know that a lot of people do machine learning or doing a lot of stuff with like, coming up with these sort of models. But I mean, it's probably unlikely that the brain does anything like back propagation, that there's a lot of like dynamic activity. So different, temporal speeds of things firing. Like the whole idea of, machine learning right now is that all the units are kind of updated in step. So it's all synchronized. But I mean, the brain has alpha waves and beta waves, and like those have to matter, right? Like the speed propagation of these things has to matter. So I mean, we're getting better and better models, but I think it's probably working. Slowing down, I don't know. I think it's continued at its same pace. I just think that there was a lot of hype that deep learning, machine learning was going to just solve everything. But if you actually know something about it, you'll be like, well, it makes sense that it would solve these kind of problems, but there's a lot of problems that like I don't know how they would solve it. So there's a barrier of meaning. I don't think so. I mean, I think I don't buy into that argument. I guess you could say that like that there's something human about that. Um, well, I mean, artificial intelligence, like it's not like machine learning is a subset of techniques, I would say, within the field of artificial intelligence. Um, would I consider myself an autodidact? Well, an autodidact is someone who teaches themselves things, so I guess I am, unless there's some more specific definition I'm missing. Uh, yeah. No, I think, I don't know. Machine learning is very interesting to me. I did cover it a bit in the MIT challenge. I feel a little bad that I didn't go more into it. I have done a little, I took Andrew Ng's class on Coursera. And I did like that class, but I don't think I did all of the assignments and stuff. So I would like to do a machine learning project. I do find it very interesting. I think my interest is much more on understanding how the mind works than on building some kind of, crazy application or something. Yeah, and you know what? And that's one of the things is that I feel like a lot of people talk about how, oh, they're not motivated to study and these kind of things. I think people are very sensitive to competition. So if you feel like you are being directly compared to some reference group and you are worse than them, I think the brain just has this evolutionary mechanism of like, don't spend time on this thing, that when you're bad at something relative to other people, like it's always trying to help you seek relative advantage. And so I think self-education is often helpful because you're removing yourself from that competitive environment. So you don't have like it's just the challenge on its own. Entering academia. I did think about doing a PhD for a while, and the more I thought about it, the less appealing it is, just because to me, a PhD is mostly training for a particular type of job doing research. And I'm not sure whether that's what I want to do. I kind of like doing what I'm doing now. I'm more interested in the learning of things than doing research. I mean, I might get to some point with some subject that I would like to go into that, but I just don't see it right now. I think if I were to do a PhD, it would be something with cognitive science, though. Maybe neuroscience, maybe some kind of computational and computer science end. Mm. Mm. Definition of an autodidact: someone who teaches themselves mostly everything. I don't know. See, here's the thing. This was a big thing that I was talking about. Was the MIT challenge self-education? And that was something that when I was doing it, I mean, from an outside definition, I was doing it on my own. I'm not enrolled in school, so kind of by a simple definition, of course, it's self-education. But on the other hand, I'm taking courses. I have all this material. Like this is, like I feel like I wasn't having a radically different experience from MIT students in a lot of classes. So there's a sense that I was, no different from someone who's taking formal education, or not that different from someone taking formal education. So I think the definition of what makes someone an autodidact is kind of loose, because even when you're in a university, you're teaching yourself a lot of things with the resources. And when you're outside of a school, you're teaching yourself a lot of things. Not to mention you are, you're doing things that are, when you're doing self-education, you're using books, you're using resources. So I think you're always kind of interacting with a teacher. The person who's truly self-taught, that like has never encountered anything and they just learn from just pure trial and error and feedback, like those people are exceedingly rare. I've yet to encounter almost anyone who's like that. So, I mean, using the looser definition of autodidact, I think most people are. So PhD allows you to do research on the cutting edge. You can take that on an entrepreneurial route. Well, I'm already on an entrepreneurial route. Like I'm already running a blog and business. I'm already a writer. I mean, this was kind of the thing that after I finished the MIT challenge, like I could have continued going and trying to do that, but I also wanted to continue writing and continue doing that. So, I mean, definitely for some people doing that would have been a good thing. But I think for me, I've found what I want to do. And so this learning is more to support my current work and stuff. Yeah, I think you can do an entrepreneur. Like that's, Sergey Brin, Larry Page. That's what they had to Google was PhD, and then they went off to that. So I think definitely doing a PhD can be a leapfrog into doing high tech. Captain Marvel's asking, when I'm on my own, I learn a lot, but when in school, I feel like I have to choose between learning or a good grade. I don't see why you feel like you have to choose. I feel like the two are not as different as they would seem. I mean, maybe it depends on your class, but maybe you have to think about your studying strategy. I mean, I think that there's quite a bit of overlap. I think if you're learning well, that tends to correspond with having good grades. Depends on the class. I mean, some classes just have really bad testing mechanisms, and so you have to learn for the test. But I mean, I would say that there's a lot more overlap than not. Instead of basing businesses on existing knowledge. Well, I mean, I don't know. Like you could say I have a business, but my business is kind of a writing teaching profession where I sell courses and write books and stuff. And so I like that because it's constantly, I'm always learning. I'm always trying to expand my knowledge so that I can teach better and do those things better. So, I mean, it's not the same as coming up with some very narrow technical solution and then expanding that into a business, but it's also a way that you can pursue a career. Don't want to study like you study in the evening. I don't study in the evening, so that's one way to avoid that. Yeah, I mean, yeah, there's always times where you don't want to do it. But yeah, if you keep putting in the effort, I think it's helpful. Like I've talked about this before about how I like try to set these challenges so that there's enough pressure so that I'm not procrastinating too much. And I get used to doing the schedule where I have, burst, and then time off in the evening, or burst during the week, and then hopefully weekend off. Maybe not this weekend, but I do it that way just so that I can have that kind of work intensely, time off. And I mean, it's hard to get into that rhythm sometimes because if you didn't procrastinate a lot, then you feel guilty even in the evening. But it's all about, like, habits kind of have this bootstrapping problem that once you're in the habit, it's sort of self-sustaining. And so I feel like my studying rhythm is kind of self-sustaining because, but it can degenerate if you start being lazy and slack off, and then you feel like you have to work later. So I've enjoyed chatting with you guys. I'm going to have to run. I've got some stuff I got to do this evening, but I will be back tomorrow morning. And I'll be back to continue working on these problems, finish off 7.5. This is where we're at. This is where I'm at right now. Got these guys left to do. Hopefully I can get these guys finished by Friday. There's still a few more refinements I want to do here. We'll see. I might work a little bit on the weekend, but I'm going to try to work as much as I can get to Friday because it would be nice to just relax and then work hard again Monday, Tuesday. I think a lot of things people think are hard are not really hard. Getting in the habit is hard part. Habits are only hard for a little bit. Yeah, habits do require work to sustain, but the work goes down as you keep doing them. So if you can read my post on metastable habits, I would say that, yeah, and you want to look for self-sustaining cycles. So this class has been tiring. Like if I had to do this perpetually at this pace, it would tire me out. I felt the same way when I was doing the MIT challenge, that like my energy level was dropping off. So there is an effort component. But if you pick the right way of doing things, you can sustain it for a lot longer. Why do I write down facts? I've been doing some flashcards too. So got some flashcards here. Just for like trigonomic identities, a few eigenvalues, eigenfunctions, things that I've been like, oh, right, I need to remember that. So I got about, I don't know how many do I have here, about 20, 16, 15, not a lot. It's not that many. All right, well, I'm going to get going. Thanks, guys. I'll see you tomorrow.